Right now, in a research campus outside Beijing, engineers have switched on a wireless network that moves data at 1 terabit per second, roughly 100 times faster than the 5G signal in your phone right now. At that speed, you could download a 2-hour movie in the time it takes to blink. Not a slow blink, a normal one. You heard that right. And the wildest part isn't the number. It's that this isn't a slide in a pitch deck or a render on someone's laptop. It's real hardware, moving real bits through real air. The race to build the next internet has quietly already started, and one country showed up years early. The number that broke the benchmark. Let's start with the terabit, because it's the figure that set the internet on fire. In late 2025, researchers in Huairu, a district on the northern edge of Beijing, reported running what they described as the world's first 6G terahertz trial network. And it hit a peak downlink of around 1 terabit per second, with ultra-low latency to match. 1 terabit is 1,000 gigabits. Your home fiber connection, if you're lucky and you live somewhere nice, might deliver 1 gigabit. This trial moved 1,000 times that through the air, wirelessly. Now, here's where I have to put my honesty hat on early, because the title of this video says 100 times faster than 5G, and I want to be precise about what that means. When 5G itself arrived, it was billed as roughly 20 times faster than the 4G standard it replaced, a genuine generational leap that reshaped everything from video streaming to mobile gaming. 6G is aiming to make that leap look modest. A good 5G connection in the real world delivers somewhere in the low hundreds of megabits per second to a phone, with theoretical peaks around 10 to 20 gigabits under perfect lab conditions. So, depending on whether you compare peak to peak or real world to real world, 6G's terabit target lands somewhere between 50 and 100 plus times faster. The International Telecommunication Union, the global body that actually defines what counts as a generation of mobile technology, has set a peak data rate target for 6G of exactly 1 terabit per second. So that Huairou network didn't just hit an impressive number, it hit the number, the one the entire world agreed would define the finish line. And it's not a lonely result. This is the part that should make everyone sit up. In China, the terabit headline sits on top of a whole pyramid of smaller, verified records. Purple Mountain Laboratories in Nanjing, working with Southeast University, China Mobile, and Fudan University, demonstrated real-time terahertz wireless transmission at a net rate of over 200 gigabits per second using a dual wavelength system, which the lab called the highest publicly reported record of its kind at the time. Multiple Chinese teams have now independently pushed real-time terahertz links past 100 gigabits per second. That Purple Mountain result wasn't a one-off stunt either. It was backed by a special government project on as yet unstandardized 6G systems, and the team immediately pointed to where it leads. The same terahertz technology could integrate with existing fiber optic networks to deliver 100 to 1,000 gigabit indoor and outdoor access, replace tangles of cable inside data centers, and slash the cost of network infrastructure. When one lab hits a wild number, that's a breakthrough. When half a dozen of a country's top institutions, Purple Mountain, Southeast University, Fudan, Pengcheng, Tsinghua, Peking University, plus the muscle of China Mobile, are all clustered at the frontier, publishing in Nature and pushing each other month after month, that's not a breakthrough anymore. That's an industry with a head of steam. But speed alone doesn't explain why engineers around the world are nervous. To understand that, you have to understand the strange, almost unusable slice of the electromagnetic spectrum that all of this depends on. And it's a slice that, until recently, nobody could tame. The ghost frequencies. Here's the physics problem sitting at the center of the entire 6G story. Every generation of wireless has done the same basic thing to go faster. climb higher up the radio spectrum into frequencies with more room to carry data. 4G lived in the low gigahertz range. 5G climbed into the millimeter wave band up to tens of gigahertz. And 6G is reaching for a band that engineers have eyed for decades but never seriously used for communication, the terahertz range, roughly 100 gigahertz to 10 terahertz, sitting in the no man's land between microwaves and infrared light. Why go there? Because bandwidth is everything, and the terahertz band has bandwidth to burn. Where 5G's millimeter wave channels offer a few gigahertz of width, the terahertz band offers 10 times that or more. More width means more lanes on the highway, and more lanes means terabit speeds. It's the single richest stretch of unused spectrum real estate on the planet. There's just one catch, and it's a big one. Terahertz waves are fragile, absurdly fragile. They're so easily absorbed that they barely make it through open air. A little humidity, a rain shower, fog, a muggy afternoon, and the signal drops off a cliff. They struggle to pass through walls. They don't like to bend around obstacles the way lower frequencies do. Point the antenna a few degrees wrong, and you lose the connection entirely. For decades, engineers looked at the terahertz band the way sailors used to look at an uncharted reef. Enormous potential, absolutely no way through. These were the ghost frequencies, full of promise, impossible to hold on to. To use them at all, you need almost impossibly precise engineering. Pencil-thin beams aimed with extraordinary accuracy, massive antenna arrays that can steer those beams electronically in real time, a technique called beamforming, and hardware that can generate and detect these delicate waves without drowning them in noise. Because the beams are so narrow and the signals so directional, the network essentially has to aim a laser-thin thread of data at a moving target and keep it locked continuously as you walk down the street with a phone in your pocket. Lower frequency signals spray out in all directions and forgive sloppy aim. Terahertz punishes every millimeter of error. This is why terahertz communication sat in textbooks for years as a someday technology. Making it work in a laboratory in real time at these data rates is a genuinely staggering piece of engineering. And it's exactly what those Chinese labs just pulled off. But a beam of terahertz radiation crossing a lab bench is one thing. Shrinking all of that down onto a chip small enough to fit in a phone, that's a completely different mountain. And in the autumn of 2025, a team climbed it. The chip that does it all. In September 2025, a team led by scientists at Peking University and the City University of Hong Kong published a result in the journal Nature that made even skeptical engineers stop scrolling. They'd built what's been described as the world's first all-frequency 6G chip. Let me explain why the word all-frequency is doing so much heavy lifting there. Normally, a device that wants to talk across many different frequency bands needs a separate specialized component for each band. A little forest of chips, each tuned to its own slice of spectrum, each adding cost, size, and complexity. It's clumsy, it's power hungry, and it does not fit gracefully into a slim consumer device. This chip throws that whole approach out. Measuring just 11 millimeters by 1.7 millimeters, smaller than a grain of rice with delusions of grandeur, it operates continuously across an enormous range, from 0.5 gigahertz all the way up to 115 gigahertz. That span covers everything from the microwave frequencies your current phone uses right up to the doorstep of the terahertz band. One chip, the whole spectrum, and it delivers wireless data rates exceeding 100 gigabits per second while doing it. The trick behind it is genuinely clever. Instead of relying purely on traditional electronics to handle these punishing frequencies, the chip uses a hybrid silicon photonic design. It marries optical and radio technology on a single sliver of silicon. Radio signals get converted into optical signals, processed as light, and then converted back. Light is fantastic at carrying enormous bandwidth cleanly, so borrowing photonics to do the heavy lifting sidesteps a lot of the noise and distortion that would wreck a purely electronic chip at these frequencies. The researchers called it one of the first verified demonstrations of a fully integrated terahertz capable transceiver that can operate across multiple bands at once. The potential uses they pointed to read like a wish list for the next decade: autonomous systems, industrial automation, and immersive virtual and augmented reality, all powered by ultra low latency links. The team was also careful, to their credit, to note that a single all frequency chip is a significant breakthrough, but the technology is still in its early stages. That honesty matters, and we'll come back to it, because the distance between a Nature paper and a mass produced consumer chip is measured in years, not months. Why does this matter more than any single speed record? Because speed records happen on lab benches the size of dining tables. A chip a few millimeters wide is the thing that eventually goes into a phone, a car, a drone, a factory sensor. This is the bridge between the physics demo and the product in your pocket. It's the difference between a rocket engine on a test stand and a rocket that actually flies. Still, even the world's cleverest chip is useless if it can only talk to the phone on the next desk. The terahertz signal's fatal flaw, that it dies over distance and can't punch through walls, doesn't go away just because you shrank the hardware. So, how do you build a network out of something this fragile? The answer is that China isn't building the network only on the ground. It's building part of it in space, building the network in the sky. If terahertz can't travel far and 6G needs to reach everywhere, you have a contradiction. And the way modern network engineers are resolving it is one of the most ambitious ideas in the whole field. Don't think of 6G as a ground network at all. Think of it as a single fabric woven from ground towers, high altitude platforms, and satellites. What the industry calls a space terrestrial integrated network. The vision is that your device connects to whatever layer makes sense. Dense city center, terahertz, small cells on every lamppost, delivering blistering speeds over short hops. Middle of the ocean, a mountain trail, a desert with no towers for 300 miles. A low Earth orbit satellite picks up the same call seamlessly. No dead zones. No, I'll text you when I get signal. The International Telecommunication Union has baked this idea, ubiquitous connectivity, directly into its official framework for what 6G is supposed to be. And China has been busy laying the groundwork in orbit. Back in early 2024, China Mobile, the largest mobile operator on Earth by subscribers, launched what it called the world's first test satellite built using a 6G design architecture into low Earth orbit at an altitude of 500 kilometers, hosting a distributed, autonomous 6G architecture. That launch didn't go up alone. A second satellite carrying China Mobile's 5G technology went with it, part of a deliberate effort to test how satellite and ground networks knit together. Low Earth orbit satellites flying just a few hundred kilometers up, rather than the tens of thousands of kilometers of traditional communications satellites, offer far lower latency and far higher data rates, which is what makes them viable as a real layer of a mobile network rather than a slow last resort. Then, in August 2025, Pingcheng Laboratory and the Harbin Institute of Technology in Shenzhen reported a breakthrough in digital beamforming for low Earth orbit satellites, with orbital field tests, dozens of them, improving signal to noise ratios by up to 5.5 decibels on transmission and 2.6 decibels on reception. In plain terms, they made the fragile connection between a fast-moving satellite and the ground meaningfully more reliable, a critical piece of stitching space and ground into one seamless network. Chinese planners describe this as extending the national computing power network into space, which is a very Chinese way of saying they intend for the sky itself to become part of the internet's backbone. Why go to all this trouble? Because whoever controls the integrated space and ground architecture controls the parts of the planet that terrestrial networks never reached: oceans, poles, disaster zones, the entire rural developing world. By some Chinese state media projections, by 2040, the number of connected 6G terminals could grow more than 30 times compared with 2022, with monthly data traffic surging more than 130 times. That is not a market any nation wants to show up late for, and China clearly has no intention of doing so. But all this raw capability raises the obvious question. A terabit per second is a preposterous amount of data to send to a human being who mostly wants to watch videos and argue online. So, what is all this speed actually for? What a terabit is actually for. Here's the thing nobody tells you: 6G was never really designed for faster video downloads. If all you want is smooth streaming, 5G already does that fine. The terabit era is about applications that literally cannot exist at today's speeds, the ones sitting just past the edge of what's possible. Start with holograms, real ones, not a shiny video on a flat screen, but a three-dimensional person appearing in the room with you, rendered in real time that you can walk around and look at from any angle. The data required to transmit a live, full motion, three-dimensional human is staggering, orders of magnitude beyond a video call, which is exactly why it doesn't exist yet. Terahertz bandwidth is one of the few things that could carry it. Every serious 6G roadmap, from the standards bodies to the equipment makers, lists holographic communication as a headline use case, and it's the reason terabit speeds aren't overkill. They're the minimum entry fee. Then there's the tactile internet, networks so fast and so low latency that touch itself can be transmitted. Picture a surgeon in one city operating on a patient in another, using robotic instruments that relay the exact resistance of tissue back to the surgeon's hands in real time with no perceptible delay. 6G targets latency below a tenth of a millisecond, faster than the delay of your own nervous system, faster than the time it takes a signal to travel from your fingertip to your brain. At that point, distance stops mattering for skilled physical work. A specialist's hands could be anywhere on Earth. The same ultra responsiveness underpins another headline use case the standards bodies keep listing: digital twins, living, real time virtual replicas of factories, cities, even human bodies, updated continuously by torrents of sensor data. You can't run a faithful digital twin of a running factory on a network that stutters. You need one that never blinks. And then there's the quiet one, the feature that might matter most: sensing. This is the idea the industry calls integrated sensing and communication, and it turns the network into a giant radar. Because terahertz waves interact so sensitively with objects and materials, the same signal that carries your data can also map the physical world around it, detecting motion, imaging shapes, even peering inside a sealed box. Huawei's research team demonstrated a terahertz prototype that used the network signal to scan and image an object hidden inside a closed container, achieving millimeter level resolution. Imagine a network that doesn't just connect your car, but sees the pedestrian stepping off the curb before the headlights do. That's the direction. The network stops being a pipe and becomes a sense. So the capability is real, the applications are genuinely revolutionary, and China is unmistakably at the front of the pack, which is exactly the moment I have to pump the brakes. Because if I sold you the hype without the fine print, I wouldn't be doing my job. The honest part: why it's not in your phone yet. Let's talk about everything standing between these lab records and the phone in your hand, because the gap is wider than the headlines suggest. First, and most fundamentally, none of this is standardized yet. A speed record in a lab is not a technology you can buy. For any of it to become a real global network, the world's engineers have to agree on a common rule book, the standard, so that a chip made in one country talks to a tower made in another. That process, run through bodies like the ITU and 3GPP, is only just beginning. China itself says it aims to commercialize 6G around 2030, and even that is an ambitious target, not a promise. Every honest expert in this field will tell you the same thing. Right now, all nations are still at the early stage of research. Nobody has a 6G network you can join. Not China, not anyone. Second, the physics I described earlier didn't go away. Terahertz signals still get swallowed by rain, blocked by walls, and lost around corners. Making a link work across a controlled campus in Huairu is a real achievement, but blanketing a messy, rainy, obstacle-filled city with reliable terahertz coverage is a vastly harder problem, and it may require an almost absurd density of small cells, one on practically every lamppost and doorway. That's an enormous, expensive infrastructure lift. Third, there's power and heat. Pushing terabits through silicon generates real thermal load, and managing energy efficiency at these frequencies is an unsolved engineering headache. A 6G base station that guzzles electricity or a phone that cooks in your hand is not a product anyone ships. Fourth, and this is a China-specific hurdle worth naming, advanced 6G devices will need advanced semiconductors, and Chinese firms face real constraints on access to the most cutting-edge chip making. Building the future network on domestic silicon is a challenge that sits partly outside the labs and squarely inside global politics. And fifth, the quiet doubt haunting the whole endeavor. Some analysts openly question whether 6G is being driven by genuine market demand or mainly by high-tech competition between nations. 5G, remember, was sold with sweeping promises and then under-delivered for years in the real world, hobbled by coverage gaps and cost. There's a real risk that 6G repeats that story, dazzling in the lab, disappointing at the checkout counter, at least for the first few years. None of that erases what's been achieved. It just means the achievement is a starting line, not a finish line. And it's precisely because it's a starting line that where a country stands right now matters so much. The race nobody else is ready for. Here's why the title of this video says, "The world isn't ready." And I mean that as an observation, not a boast for anyone. Standards are where the real power lies. Whoever writes the most patents into the global 6G standard doesn't just get bragging rights. They collect licensing revenue and shape the architecture of the next internet for a decade or more. It's why the head of the China Mobile Research Institute has been blunt that 6G won't be a simple evolution of 5G. It'll demand breakthroughs in architecture and integration, with 5G advanced and 6G developing side by side to get there. It's why China began formal 6G technology experiments back in 2022 and moved into a prototype validation phase running to 2027. This is a country treating a technology that won't launch until 2030, as if the deadline were tomorrow. And it's genuinely a race, not a walkover, which is the part the hype tends to flatten. Japan and Finland have joined forces on 6G research, with Nokia in the mix. South Korea's LG has run its own successful outdoor terahertz tests. The Next G Alliance in North America, Europe's research programs, the equipment giants, everyone serious is running hard. That very same all-frequency chip that made headlines, it was a collaboration reaching across the Pacific, a reminder that the frontier of this science is still, for now, international. This is not one nation sprinting alone down an empty track. It's a pack, and China happens to be near the front with a lot of momentum. So let's zoom all the way out and see the whole board at once. A terahertz trial network in Beijing touching 1 terabit per second, the exact figure the world agreed would define 6G. A rice grain chip that spans the entire usable spectrum from microwave to the terahertz doorstep. Satellites in orbit built on 6G architecture stitching the sky into the network. Applications waiting in the wings, holograms you can walk around, surgery performed across continents, networks that can see. And underneath all of it, a standards race whose winner will quietly tax the next internet for a generation. The terabit is real, the chip is real, the satellites are real. What's still unwritten is the rulebook that turns a handful of stunning lab results into a network the whole planet plugs into. That rulebook gets written over the next few years, and everyone building toward it knows the stakes. The rest of the world is still finishing its 5G rollout, still arguing over whether 6G is even necessary. And while that argument drags on, one country has already switched on the future in a lab outside Beijing, and it is not waiting for anyone to catch up.